All right, now that we're awesome at finding angular momentum of something moving in a straight line, let's kind of combine a few things here. So this is supposed to be a problem about a kid jumping onto a merry-go-round and getting it to spin. So it says a merry-go-round is on a frictionless axis through the center. So here's the axle there, and the thing's going to spin like this. It gives us how big it is, radius and mass, and moment of inertia of a disk happens to be 1/2 mr squared. And a former student of mine, it says Sean Malone, 72 kilos, runs 8 meters per second, and he jumps on. One thing before we start with this is, suppose Sean can run 8 meters per second, to think about what would be the best way for him to come in and jump on, right? He really should have gone in this way. That would have been the best, to run and then hop on this way. Going straight at the axis would have been a terrible idea, right? Then you just land on there and it doesn't rotate. And that would be because you wouldn't have any angular momentum around that axis. But here he does, because he's not going straight at the axis. So what we're supposed to do, it says calculate the period for one rotation of the system, Sean in the merry-go-round, after he jumps on. So this is the rotational version of a collision, okay? And so what's going to happen is Sean comes in and leaps onto this thing. Now, normally in a collision, you can conserve linear momentum, right? When you have like carts bashed together. The reason you don't do linear momentum here is there's actually an external force on the system from the axle. So he's going to come in, Sean's going to come in and jump on. And if this thing were free to move, then yeah, the whole system would like take off this way, but it's not able to. So we don't conserve linear momentum because there's an external force from the axle. So we don't conserve linear momentum due to external forces. So you don't want to do that. And you don't want to be trying to conserve energy either. We'll check that at the end, because when he jumps on, it's going to go clang and it's going to make noise. So don't be saying E before is E after. But we do get to conserve angular momentum. There won't be any external torque because any forces from the axis are right at the axis. So the thing will just should just be able to spin. So what we can do is we can say the angular momentum before equals the angular momentum after. We're going to do it that way. And so let's find the angular momentum before. Well, that's going to be Sean running in. We're going to treat Sean as a point mass. Okay, maybe I'll put that under here. This is Sean as a point mass. Right, and so what I would do is maybe the MV perp R version. In other words, only the part of his velocity that's really going this way is what matters. So that's like the V perp. Here's where he jumps on. So the part of his velocity that's this way doesn't matter a bit. So this is our guy, and what's that going to be? 8 cos 30? 8 cosine 30 degrees. So in fact, even priming this on this side, we can even start putting some numbers. This is going to be Sean's 72 kilos, then times 8 cos 30. And then how big is this thing? Radius 1.5 meters. So there's the angular momentum brought by Sean into the system. It's out of the page, and that's why the whole system's going to rotate like this after. Then afterwards, now what's going to be rotating is Sean and the merry-go-round. So it's going to be like I total. So it's going to be I omega. Maybe underneath here I'm just going to put I total omega. And then what we can do is we can split that up into I of Sean plus I of the disk times omega. So Sean comes in with like angular momentum, and then all that angular momentum is maintained in the system, and it starts to rotate around. So let's put in the pieces. The moment of inertia of Sean, he's basically going to be a point mass on the outside of this thing. So he's going to land here and start cruising around after he gets on there. And so we're going to treat him like a point mass, so that's just mr squared. Maybe I'll show one more line of algebra here. M Sean r squared. And then the moment of inertia of the disk is 1/2 m disk r squared times the omega, which we don't know yet. I'm just gonna double check that I'm not getting too low on the board for the video. It's probably getting close. What we should be able to do now is just plug in the numbers, just in case. I'm gonna maybe adjust this down. I couldn't really tell. Well, let's just finish putting the numbers in. So we got 72 times 8 cos 30 times 1.5 equals 72 times 1.5 squared. You know what? Let's take out the r squared. So we'll go mass of Sean is 72 plus half the mass of the disk. The disk was 200. So that's going to be 100 is half the mass of the disk, and then r squared is going to be 1.5 squared. Yeah, it was 1.5. Yes, that's all that, and then times omega. And so then what that's going to let us do is solve this puppy for omega. So we got some calculator punching to do. Looks like one of the 1.5s to go away. That's going to save me some trouble. Let's get rid of that. So let's go 72 times 8 cos 30. That's all that part. What do I got to do? Divide by 172. Then I got to divide by 1.5. So that's supposed to be omega. I get 1.93 radians per second. 1.93 rads per second. Let's see, 2 pi per second would be all the way around, so that's like 6.28. So this thing isn't rotating super fast. I guess that makes sense for a pretty heavy merry-go-round. Somebody just jumps on there. Let's see, we're supposed to get the period of one rotation. So what we need to do, we need seconds per rotation. So we basically have 1 second per every 1.93 rads. And then we want seconds per revolution. So it looks like there's 2 pi rads per every rev. Per 1 rev. So I'm just doing a unit conversion. So it looks like I gotta go 2 pi divided by 1.93, and that'll be how many seconds it takes to go around. So 2 pi divided by 1.93. Looks like 3.26 seconds to go around. 3.26 seconds per rev. All right, so he runs and runs, he jumps on clank, 1001, 1002, 1003 in a little bit, and then he's back. So that's kind of a mixture of using angular momentum of like a moving point mass and angular momentum of like objects rotating around an axis. I'm not going to do this right now, but I do want you guys to check it. Is check the KE before and after. Okay. Let me tip the phone up a little bit. At the bottom of the page, like where you got some room, check the KE before, which is just going to be 1/2 m Sean v squared. Just check that, and then your KE after is going to be 1/2 I total omega squared. And what you'll see is, of course, it's going to lose energy when he jumps on there, but see how that actually plays out. So again, the idea here is we conserved angular momentum in the collision. We didn't conserve linear momentum because there was an external force here. The system wasn't allowed to drift away. And definitely don't try to conserve energy when you have something clanging into something else.